So it's not a question of if it'll happen, it's a question of when it will happen.
Okay. So we owe our very existence and our position to these objects that sometimes cause a threat.
According to the Earth Impact Database, more than 160 impact craters have been identified. The largest one is called Chicxulub, Mayan for Tail of the Devil. This crater measures more than 110 miles in diameter. It was made by the asteroid that took out the dinosaurs when it crashed off Mexico's Yucatan Peninsula. Closer to home, the database also includes Meteor Crater in northern Arizona. Now a tourist attraction, this kilometer-wide hole was left by a huge chunk of cosmic iron ore that collided with Earth about 50,000 years ago. Much more recently, an enormous near-Earth object didn't leave a crater, but still made quite an impression. Packing the energy of a 15-megaton bomb, more than 1,000 times that of the one dropped on Hiroshima, it exploded over Tunguska, Siberia in 1908.
It didn't even hit the ground, but the shock wave from this airburst flattened all the trees and vegetation in the area. It was like a gigantic hand that came down from the heavens to press all the forests and trees. That's the size of the devastation of Tunguska.
If the Tunguska event had occurred over Moscow or New York or Los Angeles, the devastation would have been catastrophic, completely destroying the city and a vast area around it.
Though the chances of a Tunguska-type event happening again are remote, perhaps once every 500 years, the potential for a major disaster, if it does occur, can't be ignored. That's why NASA established the Near-Earth Object Program at the Jet Propulsion Laboratory. Its mission is to find asteroids that pose the most serious threats to Earth. The first step in stopping Armageddon.
2032 is 0.02.
Wow.
These are just nominals.
There's a 0.01.
Whenever I'm asked what are the most important aspects of the Near-Earth Object Program, I say, well, the three most important aspects are find them early, and then find them early. Because if we can find them 10, 20, 30 years in advance of a problem, we have the technology now to mitigate them.
The NEO program employs 5 full-time telescopes located across the American Southwest and around the world. They search the skies for asteroids, especially those measuring at least 1 kilometer in diameter, or about 2/3 of a mile and larger. Asteroids that big can cause worldwide devastation on impact.
We can compare the process of finding asteroids to the process of figuring out where a golf ball is going to land after it's been hit. Now just imagine that instead of being able to see the golf ball continuously throughout its entire flight, I only have a handful of freeze-frame snapshots of it while it's moving. And now I've got to figure out where it's going to go. So first of all, I've got to correctly distinguish the golf ball in the frame from all other objects in the frame, say trees or birds, or even other golf balls that may not be the same one. Once I've identified the golf ball in each of the frames, I need to use what I know about the laws of gravity to correctly fit a trajectory to it so that I can figure out where it finally lands. In the same way, when we look for asteroids, we have to just take snapshots of different parts of the sky and distinguish the asteroid from stars, from galaxies, and from any other transient phenomenon like, say, cosmic rays. Then we have to use the laws of gravity to fit a model orbit to it and figure out where it's actually going to go in the end.
No telescopes in the NEO program have found more asteroids than those at Lincoln Near-Earth Asteroid Research, Linear for short. Located in southern New Mexico, they've discovered almost half of the 5,000 known near-Earth asteroids, including about half of the 700 objects measuring 1 kilometer or larger.
One of the telescopes we use for hunting for asteroids with the Linear program is behind me. This is actually not a rather large telescope by astronomical standards. It's 1 meter in aperture. But the secret to its sensitivity is that blue square that you can see down in the bottom of the telescope. That's a charge-coupled device specially manufactured for wide-area sensitive search. And the combination of this telescope and that CCD gives us a system exceeding 1 million times the sensitivity of a human eye. This is what the sky looks like through the Linear telescope. What you can see is a number of stars here that are fixed, and also in that data there are a number of near-Earth objects. What I'm going to do now is have the process the data and analyze it to find the moving objects. What it's doing is it's clicking through the 5 frames, and in fact has now discovered a number of moving objects. What you see here are ones that look like this. These are actually main belt asteroids. They're out located in the main belt between Mars and Jupiter. They don't pose any threat at all. On the other hand, you find a couple of them that are very different. This one's in fact going opposite motion of the main belt and much, much faster. This one's going straight across. These are in fact near-Earth objects, and in fact these are 2 that Linear discovered.
Linear sends its data to the Minor Planet Center in Cambridge, Massachusetts, the clearinghouse for all near-Earth object searches.
The Minor Planet Center's job specifically is to tie the observations of new NEOs with already existing NEOs and just refine the orbits of the near-Earth objects in general. And with the orbits, other groups can go perform physical observations using various telescopes to determine the actual sizes of the objects.
The Minor Planet Center considers an asteroid potentially hazardous if its orbit brings it to within 5 million miles of Earth. That's too close for cosmic comfort, and definitely earns a rating on the Torino scale, a guide scientists use to assess the threat level posed by an asteroid.
This scale ranges from 0 to 10, where 10 is absolute destruction, and 0 means no hazard at all, or very little chance of any sort of impact. The highest rating that any object has ever received so far on the Torino scale was an asteroid called Apophis. And Apophis is named after the Egyptian god of destruction. So Apophis at one point had a Torino rating as high as 4.
In fact, in the weeks following its discovery in December 2004, there was a time period when it appeared to have as high as a 2.7% chance of impact in 2029. That's about 1 in 37. These are roulette odds, not lottery odds. And so at that time, everybody really started paying close attention to Apophis as a possible threat in 2029.
Measuring about 270 meters in length, or more than 800 feet, Apophis has the energy of a 500 megaton bomb, enough to wipe out a major city or cause a devastating tsunami. In 2029, Apophis will come closer to Earth than the satellite bringing you this TV program. Despite the unusual proximity, additional radar and optical analysis have eliminated the threat of an Earth impact, a 0 on the Torino scale. But during that orbit, Apophis may pass through a keyhole, an area in space where if the asteroid passes through it, there's a 1 in 45,000 chance of another encounter with Earth in 2036.
The possibility of a collision in 2036 is something that we're very carefully monitoring, and yet we have excellent opportunities to observe Apophis in around the year 2013 and again around the year 2021, at which time, with very high confidence, we can say that that possibility of impact will be eliminated. In the unlikely case that that possibility of impact persists, we'll still have plenty of time to avert the collision through some kind of a mitigation campaign.
Mitigation is the next step to stopping Armageddon. How do we prevent Apophis or any large asteroid from colliding into Earth and causing mass devastation? The obvious answer may be the worst option of all. Our very survival depends on the answer to this question. If we find a large asteroid on track to collide with Earth, can we do anything to prevent it from happening?
You can think of an asteroid impact as a huge natural disaster. But the thing that makes this different than the kinds of natural disasters that we know about, hurricanes or earthquakes and things like that, is that in principle it's preventable. So your job isn't necessarily how do you clean up in the aftermath, but how do you prevent it? And that's an important distinction.
Preventing a massive Earth impact brings us to step 2 for stopping Armageddon: mitigation. Neutralizing a deadly near-Earth object is no easy task. Take it from Hollywood. Or maybe not.
The worst thing to do is to look at all the Hollywood movies where we have Macho Man going out in the space shuttle, way out in deep space, planting hydrogen bombs on these objects. Well, first of all, the space shuttle can't even reach those distances. The space shuttle simply goes around the planet Earth itself. Second of all, and more important, to blow up an asteroid is the worst possible scenario. Because instead of having one monster asteroid, you now have 2, 3, 4 pieces, each piece capable of initiating tremendous havoc on the planet Earth.
On the other hand, if it were a large object and you had enough time, several years, you could try and blow it up and hope that the shrapnel would miss the Earth, or most of it would. But large objects we almost certainly would find ahead of time. It's really the small, far more numerous objects that are the ones that are tough to deal with.
If outright destruction, such as a Hollywood-style bombing, is too risky, or at best reserved for only the largest asteroids, there's a safer way to move a near-Earth object out of harm's way, and that's by deflection.
If an asteroid is headed toward an impact with Earth, you're far better off by changing its orbit very slightly so that it misses the Earth, but stays in one piece, much better off than you are trying to break it up. But you can't make anything disappear, you simply break it into pieces. Bombing it is going to break it into pieces, which could do much more damage. It's a shotgun blast instead of a rifle bullet.
To work best, deflection requires as much lead time as possible, years, if not decades. Put simply, early detection means early deflection.
More importantly, the farther away it is, the less force we have to apply in order to cause a large shift in the asteroid's orbit.
To demonstrate the point, let's play hockey. The further away from the net a player shoots the puck, the less deflection will be needed to prevent a goal. However, if a player takes a shot much closer to the net, then a much larger deflection is required to keep the puck from going in. Now imagine that the puck is an asteroid and the net is the Earth.
The preferred scenarios are to deflect the asteroid by changing its velocity. If we can do that sufficiently far in advance, for example, 10 years, we only need to change its velocity less than 1 centimeter per second. So it's very, very small change in velocity. The cumulative effect then will mean that it will get to where we are either before we are there or after the Earth is at that position, so it is no longer a problem.
To do just that, several deflection strategies have been proposed. And with apologies to Bruce Willis, none requires a manned mission.
In fact, a manned mission would significantly hinder these things. As to this point, with current technology and current vehicles, we can't really get very far away from the Earth. And that severely constrains your ability to actually solve one of these problems when the optimal time might be the opposite side of the sun to meet the asteroid.
The thing is deployed.
One deflection strategy advanced by French researchers calls for commandeering a non-threatening asteroid to knock an Earth-bound object off course. Call this strategy asteroid versus asteroid.
It's not totally outside the realm of possibility. Trying to park it where we want it and not have it hit the Earth is in itself questionable. We have only a certain number of these that are anywhere near the Earth. And finding one that could be easily moved in near Earth, obviously you're talking about the same asteroids, it might be danger of hitting the Earth to start with. And so I would not be in favor of thinking of bringing one in to have it later. And the ability to shoot a large asteroid later is very difficult. We don't need something that large to have enough energy and momentum to deflect it.
Another proposal comes from the European Space Agency. It's preparing designs for a mission named Don Quixote. Instead of tilting at windmills, the agency plans to alter the course of a non-threatening asteroid by launching a spacecraft called a kinetic impactor to collide into it.
A kinetic impactor is number one in my toolbox of what I would do. It's very simple, it's straightforward, and we at least have a bottom line, a minimum effect that we know we can count on. We can launch something large enough at sufficiently high velocity within at least, let's say, 10 years, 20 years, to deflect an asteroid up into the several hundred meter range.
Kinetic impact and asteroid versus asteroid strategies require a massive collision to deflect a threatening near-Earth object. But other proposals suggest it may be possible to stop Armageddon with nothing more than a beam of light. There are several ways to stop Armageddon. Some propose a sudden, massive impact that literally knocks an Earth-bound asteroid off course. Others suggest the mission can be accomplished without a collision by using other means, such as a standoff nuclear explosion, to push the asteroid out of harm's way.
You detonate the weapon some small distance off the surface. The main effect then is for energy, hopefully in the form of neutrons, penetrating the surface, and you heat it and you blow off pieces of the surface. It's over a fairly large area, so you diminish the chance of breaking it up.
There's one problem, though. Nukes are banned from space by international treaty. But if an asteroid threatens our very survival, will that really matter?
In terms of mitigation strategies, I'm most impressed with the use of the nuclear weapons. And I think it's the most efficient. Sure, it's not been tested, but neither has anything else that we have. And also, just from a personal standpoint, I would much rather deflect an object than sacrifice North America. And if I had to go to court afterwards, that would be just fine with me.
But you don't have to nuke an asteroid in order to nudge it. Safer methods include using solar sails. These orbiting reflectors, according to advocates, could concentrate the sun's rays on an asteroid. The heat generated would vaporize surface rock, creating a jet of material that would propel the object away from an Earthbound trajectory. Then there are lasers. If they're powerful enough to cut the strongest metal and perform delicate surgeries, then maybe a more powerful version could deflect an asteroid.
The laser is very attractive because it's more economical. It costs less, basically. It's easier to do. It could be a robotic spacecraft. The laser uses a beam of light to the asteroid, which causes material to fly off from the asteroid, which then pushes the asteroid. You don't have to carry the material up there that's going to exert the force on the asteroid. The laser can be very precisely directed. It's very gradual. It can be done over a 3-month period.
Researchers discovered a laser's potential by accident in the 80s while experimenting with short pulses on a wafer made of silicon, material similar to the surface of an asteroid.
We basically set up a movie camera and timed it with a laser so we could take step action shots of the material leaving the surface of the silicon wafer. And we were surprised to discover what we found. That is, we can actually see these chunks of material coming off and see them vaporize. It was a scientific discovery as well as a new technology.
As significant as that discovery was, it's still a big leap from a silicon wafer to an asteroid. But it's one that can be made, proponents claim, with a laser pulse 5,000 times more powerful than those we use every day on Earth. This super laser, powered by existing rockets and solar panels, could park as many as 5 kilometers away from an asteroid, then use a series of short pulses rather than a continuous one to deflect it.
The reason for the pulse is that the very short pulse can deliver enough intensity to the surface of the asteroid so that the material explodes off from the asteroid. When that material explodes off from the asteroid, it pushes the asteroid in the direction that you want to send it. You also need the very short pulse because as the laser pulse strikes the surface of the asteroid, it creates a cloud of material that emerges from the asteroid. That cloud of material will absorb any additional light that's sent to the asteroid. So it's extremely important to get all of the light energy into that area of the asteroid in that very short time before that black cloud forms.
To some experts, lasers and even solar sails could work, at least in principle. The intense light they both emit is adjustable and adaptable to all types of asteroids, and the ejected material, mere puffs of dust, would pose no threat to Earth. But their potential drawbacks could prove prohibitive.
Keeping the laser source or a large solar mirror in the correct place is very difficult to do and has to be done for a long time. With regard to the solar reflection also, then there's a question of the dust that's blown out. What is it going to do to the solar mirror? And so there are significant long-term problems. And so whether that could be done in the future, we don't know. At the present time, it's certainly outside of our capability.
There are continuous lasers now that produce more power, 25 kilowatts, 50 kilowatts, that have been made for military purposes that have more power than is necessary. The kind that we're proposing would require taking the ultra-short pulse lasers and increasing the power up to at least 5 kilowatts, maybe 10 kilowatts. A focused effort could probably do this within 5 to 10 years, could actually be done if there was an intent to do so.
And why stop at just one laser? One day, a fleet of them could be permanently stationed around Earth to act as a defensive shield against asteroids that threaten us.
It would avoid the danger of having a last-minute scramble to solve the problem and having to send up nuclear devices, nuclear weapons into space, trying to blow up the asteroid, which is probably a bad idea.
Lasers show potential as asteroid deflectors, but it'll be a long time before they're a viable option. Until then, there's another mitigation proposal that deserves serious attention. It's the brainchild of two former astronauts who insist it's the only real way to stop Armageddon. Of all the proposals to stop Armageddon, the most effective one may be a contraption called a gravity tractor. For such a complicated undertaking, it operates on a very simple principle.
We know that everything out there in space has a gravitational pull. So asteroids themselves have a gravitational pull. And we also know that a spaceship interacts gravitationally with the asteroid. So if the spaceship were to come close enough to the asteroid, it could then begin to attract the asteroid slowly out of its course, if we can get it in time.
Developed by the B612 Foundation, named after the asteroid in the literary classic The Little Prince, the gravity tractor is gaining popularity due to the efforts of its chief advocates, two former astronauts, Ed Lu and Rusty Schweikert.
The gravity tractor is a very weak deflection concept, but it's very precise. And so we don't recommend using it for what we call the primary deflection. That is, to make the asteroid miss the Earth. But once you've done that with a kinetic impact, which is a very imprecise maneuver, then you come in with the gravitational tractor and you make a very precision adjustment on what you've done with the primary deflection.
The gravity tractor is one of the very few asteroid deflection mechanisms that is in any way realistic. The only two that are probably realistic right now are kinetic impactor, where you just basically run into the asteroid with a spacecraft, or the gravity tractor. Apart from those two, most of the rest of those are pretty much science fiction.
Using mostly existing technology and powered by a combination of ion engines and solar panels, the gravity tractor itself is about the size and weight of a golf cart. Not very large by spacecraft standards, but it's still big enough, according to its proponents, to finish the job after a kinetic impact.
This asteroid is spinning around an axis or tumbling, whatever, and I come up with the gravity tractor and I basically park here. I want to pull it in that direction. So in spite of the fact that it's tumbling, I don't ever touch it. I just pull up in front of it, if that's the direction I want to pull it, and I just stay there while it's tumbling. Let's say if the asteroid itself is 300 feet in diameter, then we would want to hover something like 250 feet from the center of gravity of that asteroid. In other words, about 1.5 radiuses out from that tumbling asteroid. I don't let the gravity of the asteroid pull me in. I have to fire my ion engine thrusters off to the side so I don't blast it. And by doing that, I stay right there for a week, a month, a year, whatever it takes. Ion engines go for long, long periods of time. And now, because I have a radio transponder in my gravity tractor, the Earth can track me very precisely, and I know exactly the change in the orbit that I've made to the asteroid itself. You're reshaping the solar system without ever touching anything.
That ability to make controlled, precise movements is the gravity tractor's chief asset.
What you need to do is make sure that after you've deflected any asteroid, that it doesn't come back and hit you at a later point. What a gravity tractor allows you to do is to measure precisely exactly where it's going and to make tiny corrections to it so that you are very certain that it is not going to come back and hit you.
Despite this advantage, the gravity tractor's major drawback is its very small force. Maybe too small to make a difference on a really big asteroid.
The gravity tractor takes a long time and a small asteroid to be effective. It would have to be much smaller than 1 kilometer, perhaps 150 meters, 300 meters, something on the size of Apophis or smaller. If we're talking about a need for a larger asteroid and we don't have as much time to devote to it, then gravity tractor is probably not the method of choice.
But it turns out that the expected time between when you find that an asteroid impact is possible and when the actual impact is going to happen is many decades. So most of the time, you have time to use such a thing.
By the time we get hit by something that big, we're going to have technology we can't even imagine now. So there'll be something else and not the gravity tractor. But if we had to do it now, we could do it. The point is that we can protect the Earth right now from asteroid impacts if we do our work.
To demonstrate the gravity tractor's effectiveness, the B612 Foundation aims to perform a test deflection on a non-threatening asteroid by the year 2015.
That's really important because if we find an asteroid that's uncomfortably close to hitting the Earth and you decide that you have to deflect it, that's not a good time for your test flight. You want the test flight to be done beforehand so you work out any possible bugs.
The real trick is convincing NASA that it ought to demonstrate this capability before we end up having to use it. That's the problem. You're dealing with potentially millions of lives. It's simple and cheap to demonstrate it. So let's demonstrate it, and then we know.
This leads to the third and final step in stopping Armageddon. Who decides when and what to do if an asteroid has our name on it? There are three fundamental steps to stopping Armageddon. Detection and mitigation comprise the first two. The third, and maybe most challenging one of all, is who makes the decision when to act.
Right now, if we knew something were coming, I think it's likely that we would run around and not do anything in time. I think it's important to have basically sort of the manual. When the asteroid comes, what do we do?
Answering this question gains urgency as bigger and better telescopes come online, such as PAN-STARRS, an acronym for Panoramic Survey Telescope and Rapid Response System.
PAN-STARRS is a University of Hawaii project that may well revolutionize the search for near-Earth objects. The idea is to have a very wide field telescope with a huge field of view, and so they can go deeper, that is further out in space, and do it faster and cover much more of the sky every night. New programs like PAN-STARRS are going to increase the discovery rate, and so once we find the vast majority of these objects, we can easily track them 100 years into the future and see whether or not any of them are a problem.
Some experts predict that within the next 10 to 20 years, as many as 1 million near-Earth objects could be discovered. That's in addition to the more than 5,000 we've already found. Even with this exponential increase, it's still possible that a space object, perhaps a comet, could evade detection and hit us.
Comets can literally come out of the blue. They come from the outer reaches of the solar system, and they come in, and we may only have a few years or less to mount some kind of a deflection effort. So we don't know for sure that there's no comet heading our way. But comets don't fly by the Earth very much, and so we have a very good confidence that the predominant Earth hazard is coming from asteroids.
It is possible right now that we could be hit by an asteroid that we're unaware of. There are plenty of surveys going on right now, but they're geared for finding the 1 kilometer and larger asteroids. And so there are objects down to about 150 meters that we're particularly interested in, and we've only found a few % of those. So there needs to be much more surveying in the future to find those potentially hazardous objects.
Right now, there are no protocols about what to do, when to act, and who makes these decisions in the event of an imminent Earth impact. So who has the authority and the capability to protect the Earth?
NASA's current charter is to find them, track them, and physically characterize them. What are they made of? How are they put together? They don't yet have the charter to mitigate them. You can well imagine that an asteroid impact would be an international problem. So it's going to take some international cooperation to decide who does what and when.
International decisions are extremely slow. I think it's important that countries get together and talk about a protocol for how you would make such a decision. And if they begin their quibbling and arguing at the moment they find it, they may quibble and argue all of their time away before they have to do something.
The good news is this conceivably could unify the people of the world around something that affects all of us. And we could all work together to solve it.
The whole globe is at risk, not just any one country, and not just spacefaring nations. So while the spacefaring nations may end up with the responsibility to do something, who pays for it? Who says do it? Who handles the liability? We're working with the United Nations to get them prepared to make rapid decisions.
The Association of Space Explorers, an international organization of people who've flown in space, will submit recommendations for Earth impact preparedness to the United Nations in 2009. It's a first step. Until then, let these views serve as the best informed perspectives on the subject.
We need to think in terms of this is something that's important for Earth, it's important for the children, it's important for the people who come after us, and it's our willingness to prepare at this time and to give them the tools so that should the threat emerge later on, that there will be the resources and the ability and the knowledge to resolve that threat.
We may have another Tunguska, an event that is capable of wiping out an entire city, a city buster. However, on a scale of millions of years, perhaps 50 million years, we have the possibility of a life-extinguishing event. It's prudent to take efforts today because no one knows when the next impact will come. All we know is it's coming.
Strangely enough, I am not concerned about a potential impact in the near future. I know the probabilities. It is unlikely. But it is also unlikely that you will get on a plane and it will crash, and we still spend lots of money making planes safe. We have various ways of doing that. To me, this is almost an actuarial problem. We're going to determine what the threat is and prevent it.
It's so close. For thousands of years, man has found comfort in its presence. It's been a beacon for nocturnal travelers, a timekeeper for farmers, and a location finder for sailors at sea. For some cultures, it's even been a god. It's the only cosmic body ever visited by human beings. And today, NASA is planning a permanent outpost there. But how did it get there in the first place? How did the moon come to be? The answer is more astounding and spectacular than most residents of Earth have ever imagined. At last count, over 150 moons populate our solar system. Neptune claims 13 of them. Saturn has 48. And Jupiter hosts an astounding 62. Earth, on the other hand, has just one. But it's a special one. Our moon, Luna, as the Romans named it, is remarkable in its size. It is by no means the largest moon in the solar system. Several others are bigger. One of Saturn's moons, Titan, for instance, is twice the size. But our moon is the largest in relation to its host planet.
It's a quarter the size of the Earth. It's really big compared to the Earth. If you look through a telescope at the Earth from a distance, you'd see the Earth and this other big thing. If you look at Jupiter or any other planet, you got the big planet and then little tiny moons right next to it. So our moon is so much bigger, and it's the only one of the now 8 planets that has that situation.
The relative sizes of the two bodies are close enough that some astronomers go so far as to refer to the Earth-Moon system as a double planet. The mean distance from the Earth to the Moon is 234,000 miles, a 3-day flight through space. Luna's diameter is roughly 1/4 the size of Earth's, measuring 2,160 miles. A single day on the Moon is the equivalent of 27.3 Earth days. This is because one side of the Moon permanently faces us. Luna is phase-locked with our planet. So the Moon must fully orbit the Earth in order to make one complete rotation on its axis. Sort of like children in a game of Ring Around the Rosie. They always face inward as they hold hands and move in a circle. Yet as closely related as the Moon is to our Earth, it would only take a brief visit to Luna to make it quite clear that it is in fact a very different world from our planet. And an exceedingly dangerous place.
Tranquility Base here. The Eagle has landed.
There's no air, of course, so you need your spacesuit.
Indeed, the Moon has absolutely no atmosphere at all. So there is nothing to carry sound waves. If you were standing on the Moon with a friend and tried to converse, the person wouldn't be able to hear you, except by radio.
I was strolling on the Moon one day in the merry, merry month of December.
No atmosphere also means that there are no air molecules to scatter light from the sun. So the sky is always black. and the landscape does little to help brighten the scene.
Kind of monochromatic, not much color there. The rocks are mostly gray-brown colors. It's maybe a little warmer tone in one direction, maybe toward the sun, and cooler tones, grayer tones looking in other directions, but not so colorful.
Extreme temperatures would also add to the unpleasantness of a visit. The swings between hot and cold are brutal, from 270 degrees above zero at midday to 240 degrees below zero at night. Even the moon's low gravity, just 1/6 of Earth's, could present a hazard to a tourist. A reality the Apollo astronauts kept at the tops of their minds during their many moonwalks.
But they realized that beyond the thickness of their visor in their spacesuit was death. Should they do something and fall into a rock and lose their footing and fall and hit an outcrop, this visor could be cracked, exposed to the lunar vacuum. We would have had a serious situation on our hands.
But while a spacesuit could protect lunar tourists against the vacuum of space, a lack of oxygen, temperature extremes, and lethal solar radiation, a potential hazard a spacesuit would do little to protect against is high-velocity micrometeorites. They pummel the lunar surface frequently.
Tiny meteorites, the little ones that burn up in our atmosphere and make shooting stars, there's no atmosphere on the moon, they're coming right down, hitting the surface.
They pulverize the lunar surface, generating a dusty blanket of gravel-like material called regolith. Dr. Amanda Hendricks studies the moon at NASA's Jet Propulsion Laboratory.
This plant here is kind of a regolith factory. It's ground up rock, is what it is. The timescales at this gravel mill are a lot faster. Here, it's made in less than an hour. But on the moon, it is the result of more than 4 billion years of bombardment by meteoroids and micrometeoroids raining in on the surface and breaking up the rock.
Like the product of this gravel mill, lunar regolith has formed in a variety of grain sizes, from large rocks to fine dust.
This very fine dust is familiar to us from Apollo images that were seen of astronauts' footprints in the dust. It's very fine, and so fine, in fact, that the astronauts had problems with it sticking to their spacesuits, getting into the equipment, and it can end up causing a bit of a problem.
Really big meteorites have also hit the moon in the past. In fact, these massive impacts are responsible for the dark circular regions on the lunar surface, the shapes that to many observers seem to be arranged like the eyes, nose, and mouth of a human face. They make up the illusion of the man on the moon. They blasted huge basins in the moon's surface. Some of them are 700 miles across. Dark lava eventually burst through at the impact points and flooded the basins. Today, we call these dark regions Maria, the Latin word for seas. This dates back to the 17th century when Renaissance-era observers looked up at the moon. They speculated that the dark areas might be oceans, and astronomers of the time gave the many dark spots, or seas, whimsical names.
The seas are all named after effects that were once attributed to the moon. So you have the Sea of Storms and the Sea of Crises and the Sea of Tranquility and so forth.
Some of the younger impact basins have had less time to erode, so their features are still relatively crisp. One in particular is called Mare Orientale, or the Eastern Sea. It's some 600 miles across, and the impact that created it was so massive and direct, the result looks very much like the bullseye on a target.
This Orientale scar is kind of like a bullet shot into glass, where you see all the sort of rings around it and fractures going out. People have often said if that had been on the side facing directly toward the Earth, we might have had a whole different mythology about the moon, because it would have looked like a big eye staring at us.
Three concentric rings of mountain ranges surround Mare Orientale, and some of the peaks rise to several thousand feet. They're all effects of the monster impact.
When we see mountain ranges on the Earth, they're mostly caused first by the continents moving around, crashing into each other very slowly, buckling up and creating mountain ranges, which then erode into all the spectacular shapes that we see, the Matterhorn and so forth, from water erosion.
On the moon, there are no continental plate tectonics. The surface is static.
Yet you still have mountains on the moon. And the reason is that those big impact basins, that's a big explosion, excavates a pit, throws material up on the outside, so you have these rings of mountains, arcs of mountains that surround the impact sites. But they're impact features, again, they're caused by the external forces, not the internal forces.
Another notable impact crater, much smaller than Mare Orientale, but every bit as spectacular, is Tycho. Named after a prominent 17th century Danish astronomer, this impact feature is located in the southwestern quadrant of the moon's near side.
It's in the bright area. You can almost see it with your naked eye. And when that explosion happened, as with many other craters, it shot out jets of bright, powdery dust. So there are these rays that go out from it. It's very striking.
The rays of dusty, ejected material extend some 900 miles from the Tycho impact site. A mountain of debris also rises from the center of the crater. This is a result of recoil from the asteroid strike. Some of the highly compressed material at the center of the impact site springs outward once the impacting body either ricochets or disintegrates. But long before any of the moon's specific features could be discerned through sophisticated telescopes and space travel, careful observation of lunar behavior and appearance was still vitally important to Earth dwellers. For 15,000 years at least, man revered the moon as a source of light, as a navigational guide, as a reference in agricultural pursuits, and most of all, as a convenient timekeeper. In the days before our modern systems, timekeeping was no simple task. Early timekeepers had two choices. They could monitor the sun or the moon.
If you think about trying to keep track of dates, if you use a solar calendar like we do nowadays, there are 365 days in a year, and that's an awful lot of days to keep track of. And it's not something that the ordinary person can do very well. Compare that with the lunar calendar. Everybody can tell when the full moon is, when the new moon is. You don't see the moon at new moon. You see it, it's big and round at full moon, so it's easy to tell. There are only 28 to 29 days in a lunar cycle, so it's easy to count them. And so most societies actually start out with a lunar calendar.
Early observers of the moon also recognized that our planetary neighbor has a very real physical effect on the Earth itself. The moon is responsible for the rise and fall of our ocean tides.
If we think of the moon as being this tennis ball and the Earth as being this football, okay, the tides are caused by the moon's gravitational attraction. So it's obvious, okay, so the moon kind of pulls the Earth's water towards it. And so this creates a slight bulge in the direction of the moon. What's less obvious is there's also a bulge in the direction away from the moon. So there's in fact 2 high tides every day. The other high tide you can think of as being caused by the Earth's centripetal force. The Earth and the moon are both rotating around, and that causes the water on the far side to also move out.
An extreme illustration of the difference between high and low tides can be found along the shore of Canada's Bay of Fundy. The water level from high tide to low tide drops an astounding 55 feet. For some forms of life on Earth, the advance and retreat of the tides creates useful habitats. But another of the moon's gravitational effects on our planet is directly responsible for nothing less than the continued survival of terrestrial life itself. The moon stabilizes Earth's climate. The gravitational effect of the moon keeps the degree of tilt in the Earth's rotational axis constant. This tilt is what maintains the repeatable cycle of seasons as the Earth orbits the sun. Over the millennia, with the moon's prominent and constant presence in our night sky, men ultimately began to speculate on its origin. How did it form? How did the moon come to be? In 455 BCE, the Greek scholar Anaxagoras theorized that the moon was simply a rock that was flung off by the Earth. Most of his contemporaries, on the other hand, were convinced that the moon was a god, or maybe a huge ball of fire. So Anaxagoras' notion did not get much traction. Quiet speculation no doubt continued, but no hard information about the moon came until 1609. When Italian astronomer Galileo Galilei pointed one of the first telescopes at the moon and recognized that he was looking at a landscape, the terrain of another world.
When you look at the moon through a telescope, it looks completely different from the way it looks to the naked eye. Instead of looking flat the way it does to the naked eye, it really looks round, and you can see the shadows, you can see all these craters that the naked eye does not see, and it just immediately looks like a world. It jumps out at you into 3 dimensions.
Galileo made detailed drawings of the small planet's surface and established once and for all that the moon is a solid world, not a god or a fireball. But the groundbreaking astronomer never publicly speculated on the moon's origin, primarily because his interests soon moved to other planets. Not until 1873 did the first science-based theory regarding the origin of the moon publicly emerge. It sprang from the mind of a talented French astronomer named Edward Roche.
Roche advocated what's called the co-accretion theory, which says that basically Earth and the moon grew up at the same time out of the same materials.
In Roche's day, many scientists began to believe that the planets might have formed from hot condensing clouds of gas.
It gradually contracted and cooled, and as it contracted, it would separate out rings of gas. So you'd have a ring of gas here, a ring here, and so forth. And these rings of gas would then eventually coalesce and form the planets. Roche saw the Earth and the Moon as a solar system in miniature. His idea was that the Earth starts out as a ball of gas and then cools and contracts and sheds a ring of gas that then itself coalesces and forms the Moon.
But there are problems with this theory. For one, our Moon has a much lower iron content than the Earth. If the two bodies formed from the same materials, their basic composition should be the same, but they are not. This and other inconsistencies soon led fellow astronomers to quest for new ideas to explain the existence of the Moon. In the last third of the 19th century, advanced theories about the origin of the Moon started to emerge. In 1873, French scientist Edward Roche proposed that the Moon simply formed alongside the Earth out of essentially the same nebular cloud of particles and gases. But this idea had a fundamental weakness. The Moon has a much lower iron content than the Earth. It's much less dense.
The big thing to remember about the Moon and its composition is that it doesn't have any iron core like the Earth does. So you look at the Earth, and there's a very large central area, something like half the inside of the Earth is iron, nickel iron. And that's metal that drained down to the center of the Earth when the Earth was hot, when it formed at the beginning. The Moon is more like just plain rock.
Scientists initially deduced the mass of the Moon through observation and mathematical calculations. If the Moon had formed from the same stuff that made the Earth, the iron content should be similar. It was a hole in the theory Edward Roche couldn't explain. But another idea soon followed on the heels of the co-accretion hypothesis. In 1878, George Darwin announced his fission theory of lunar origin. This idea received some attention in part because Darwin had a celebrated father. Charles Darwin, author of Origin of Species. In time, though, George Darwin stepped out of his father's shadow and became known as England's leading expert on tides. And through extensive analysis of the tide-moon relationship, George Darwin came to the realization that the Moon is gradually moving farther and farther away from the Earth.
It wasn't proved until 95 years later when astronauts landed on the Moon. They put little mirrors on the Moon. And you can shine a laser at the Moon, and the laser will bounce off the mirror, come back, and you can actually measure the exact distance between the Earth and the Moon. And the rate at which the distance is increasing is 3.8 centimeters per year.
3.8 centimeters is about 1.5 inches.
If you made a movie, extreme time-lapse, you would see the Moon moving away from Earth gradually. That's what we see nowadays.
Darwin began to consider what would happen if you reversed the process, if you ran the movie backwards. As we move backwards in time and the Moon moves closer, both the Moon's orbit and the rotation of the Earth get faster and faster.
And so, well, what happens is that eventually the Moon must coalesce with the Earth. It must hit the Earth.
The logical conclusion for Darwin was that a portion of the molten, rapidly spinning Earth must have separated from the main mass and spun off to become our moon. He immediately began work on mathematical calculations to reverse the trajectory of the moon all the way back to the Earth.
Frustratingly, he reaches a point where it gets almost to Earth, and then he couldn't work it out any farther. The mathematics doesn't let you go any farther. What you get to is a point where the moon is whipping around the Earth at a rate of 5 revolutions a day, or 6 revolutions a day. So it's just zooming around the Earth, okay? And it's about 5,000 miles away from the Earth.
Still, the mathematics did not allow Darwin to bring the two cosmic bodies into contact. The fission theory was debated for decades, but scientists eventually concluded that the relative movements of the Earth and Moon could not have resulted from it. The Earth would have been spinning too fast to account for its present rotation rate. The quest for an explanation of lunar creation continued, and a new theory would soon originate with an American. In 1909, Thomas Jefferson Jackson C. was a U.S. naval captain based at Mare Island near San Francisco. His official job was to keep the standard time for the U.S. West Coast. But C. was also a gifted scientist. As a young man, he had trained as an astronomer.
He was one of the first Americans to actually get a doctorate in astronomy. He went to Germany and got a PhD in astronomy, which was, almost unheard of back then. The U.S. was still scientifically total backwater in the 1800s.
C's duty station, Mare Island, had an observatory, and the captain's job allowed him plenty of time to theorize. He had spent time analyzing both the co-accretion and the fission hypotheses regarding the origin of the moon, and he wasn't convinced. Gradually, Thomas C. developed a completely different idea. It came to be called the capture theory. Essentially, C theorized that the moon had actually formed in a different part of the solar system from the Earth, that it orbited the sun just like the other planets, but that at some point it had moved too close to Earth and was captured by Earth's gravity.
His idea was that there's something that he called the resisting medium in outer space, which we know is not there now.
C never adequately explained what this resisting medium was supposed to be, possibly tiny particles of matter. Regardless, he was sure it no longer existed.
His idea is that for the Earth to capture the moon would have to come in from far away, and then it would hit this resisting medium and slow down, and then gradually get captured into an orbit. Maybe not at once, might take a little while, but gradually it'd be captured into Earth's orbit. It's a little bit like a bungee jumper jumping off a bridge. They'd go down, come back up, not quite as far, go down, come back up. And eventually they'd settle down at the bottom.
Thomas C.'s capture theory would certainly explain the difference in iron content between the Earth and the Moon. If the Moon formed elsewhere, its composition could be very different. On the other hand, the notion that Earth's gravity could capture and retain such a large object was unlikely, since there is no obvious resisting medium to slow down an object as big as the Moon. All three theories had significant weaknesses. The origin of the Moon remained a mystery. On July 20th, 1969, U.S. astronauts set foot on the lunar surface for the first time.
It's one small step for man, one giant leap for mankind.
They had landed their lunar module on the lava plain known as the Sea of Tranquility. And mission pilot Buzz Aldrin described the view as magnificent desolation.
Beautiful view. Isn't that something? Hey, flight out here.
The astronauts brought back pounds of moon rocks and dusty soil, or regolith. Geologists at Johnson Space Center in Houston eagerly awaited their arrival.
The excitement when samples first came back was just electric. I mean, it was just incredible. Nobody really knew quite what to expect. We realized right away that we had basaltic rocks, like one might see in Hawaii. In fact, very similar to rocks one would see in Hawaii.
The NASA geologists were intrigued to find not only basalts, but rocks of another sort. Rocks called breccias. Breccias form during asteroid impacts.
So if you can imagine a large impact body hitting the moon is going to be very chaotic. It's going to throw up debris. Debris is going to come flying out of this, what winds up to be a crater after it's over. There are many craters on the moon. This debris gets all jumbled up and lands on the ground around the crater, and then it gets compacted with the heat generated by the crater and gets turned into rocks that look very chaotic. You see all sorts of pieces in the rock of different sizes, different shapes, all pieces of the rock that were in the area that the impacting body impacted. We had just not seen anything like this on Earth.
The moon soon began to tell a fascinating tale. First, the rocks and soil samples contained particles indicating that the moon must have been covered by a deep ocean of lava after it formed. This notion was reinforced by the discovery that the rocks were lacking significantly in what scientists call volatile elements.
Volatile elements are those that can evaporate easily and they be lost when you heat up a rock. And some examples of volatile elements include water or potassium, for example. And if you compare the bulk Earth rocks to lunar rocks, you find that the lunar rocks are extremely parched. It's as if they've been heated and they've lost a lot of their volatile elements.
But along with these stark contrasts, the lunar samples also revealed at least one astonishing similarity between the lunar surface and rocks and soil from Earth.
The isotopes of individual elements, like oxygen in particular, you have different forms of oxygen. The moon had exactly the same ratios of different forms as the Earth did. But all the other rocks we knew from elsewhere in the solar system, which are meteorites that fall in space, all have different oxygen isotope ratios, which tells you that the moon material and the Earth material are very, very similar.
In the end, the lunar samples had supplied a wealth of hard evidence regarding the geological makeup of the moon. But astronomers trying to understand the moon's origin were still left with a puzzle. For William Hartman of the Planetary Science Institute in Tucson, Arizona, the information gleaned from the moon rocks supported some ideas he'd been working on for nearly a decade. Now a distinguished astronomer and painter of space images, in the early 60s, Hartman was a graduate student at the University of Arizona, taking part in a project to map impact craters on the moon. From the enormous basins, or seas, to the smallest visible dimples.
We realized during this in the 60s that the big basins are actually impact features. Very large asteroids hit the moon and made these huge explosions 600 miles across. How big an object does it take to do that? Something 100 miles across. So we had large objects running in our solar system as the Earth was forming, and they were crashing into planets.
For Hartmann, the notion that 100-mile-wide asteroids once impacted planets begged a couple of questions. Could planet-sized objects have ever collided and have something to do with the formation of the moon? By 1972, Hartmann and fellow Tucson astronomer Don Davis had created a computer program to help them explore these ideas. The program made a rough attempt to simulate the accretion process in the early solar system. The astronomers wanted to see if any other planetary formed near the Earth that could have crashed into it.
So the idea was, if there was some other body there and it finally crashes into the Earth and blows off all this crustal material from the Earth, as well as from the impactor itself, maybe the moon could form out of that.
Sure enough, the simulation showed that a second planet could have formed in the Earth's accretion zone, one about the size of Mars. It wasn't the moon, because it had formed from the same elements as the Earth and should therefore have had the same iron core and heavy density as Earth. The moon, of course, does not. That was evidence enough for Hartmann to formulate a new fourth hypothesis. It came to be called the giant impact theory. In 1974, a new hypothesis explaining the origin of Earth's moon debuted on the scientific stage. Its proponents dubbed it the giant impact theory.
The basic idea is that about 4.5 billion years ago, Earth collided with an object roughly the size of the current planet Mars. It's a very large collision, and it started the Earth spinning. It's what gave us our current 24-hour day, we believe. And this collision was so massive that it launched material into orbit around the Earth, and it's from that material that we believe the moon later coalesced.
Dr. Robin Canup and others at the Southwest Research Institute in Boulder have constructed a computer model to study details of the giant impact scenario.
It divides up the Earth and this colliding rogue protoplanet into many different particles, and then the evolution of each particle is tracked through the course of the impact.
The simulation depicts the impact from a bird's eye view from the top down.
The Earth was probably partly molten even before this impact. So initially, the impactor came in from this direction. It hit the Earth with an off-center collision. And you can see the impactor has been stretched out into this long arm of material right here.
Scientists believe the upper layers of the Earth became completely molten following the impact.
The collision starts the Earth rotating. And you can also see that the collision has substantially distorted the shape of the Earth itself. After a couple hours, we see that this arm of impactor material has coalesced gravitationally into two large clumps. The inner clump of the impactor material is actually composed overwhelmingly of the impactor's core, so that when this inner clump recollides with the Earth, which happens right there, the vast majority of the iron that came in with the impactor is actually accumulated by the Earth. While this outer clump comes in and makes a close pass by the Earth and is stripped by the Earth's gravity into a long arm of material, which then breaks up to form this disk.
The material is thought to have coalesced to form the moon in less than a year, following the massive impact. There is no sign of this impact on the Earth today, because at the time, our planet had only developed to about 90% of its current size. The remaining 10% would accumulate from later, much smaller impacts. Also, the Earth's own gravity had a reshaping effect.
Within a day after the impact, the Earth had reassumed a basically spherical shape, and any depression that the impact caused would have been smoothed over.
Giant impact theory originator Bill Hartmann presented his hypothesis at a scientific conference in 1974. But it received little attention for nearly a decade. Interest in the moon dropped off sharply at the end of the Apollo missions.
Beautiful, very smooth, very quiet ride.
Finally, at a lunar conference in Hawaii in 1984, 12 years after the last moonshot, the world's foremost astronomers reached a consensus. The giant impact theory was the most acceptable explanation to date for the origin of the moon.
I think there's still some people who say, okay, it's not really proven yet, but it's what I would call the default theory. If you look at any textbook of planetary science or geology, it's just the theory that's accepted. And there are certain small discrepancies which have yet to be explained, but by and large, it works.
Even with an agreed-upon theory of how our moon came to be, scientists have not finished studying our closest cosmic neighbor by any means. In fact, talk of returning to the lunar surface with a permanent manned outpost has recently emanated from the White House and NASA headquarters.
Gorgeous views out the window. Ink sequence good, everything go.
Such a base could provide a place to train astronauts to live in space long-term, as well as provide a more efficient launch point for eventual missions to Mars. But such lofty scientific goals are far from the minds of average residents of Earth, who occasionally peer up at the glowing, mesmerizing lunar disk in the night sky. For us, talk of lava oceans, regolith-forming micrometeorites, and giant impacts will never diminish the fascination and romance of our mysterious neighbor world, the moon.
In the beginning, there was darkness, and then, bang, giving birth to an endless expanding existence of time, space, and matter. Now see further than we've ever imagined, beyond the limits of our existence, in a place we call the universe.
Are we alone? Or is there another Earth-like planet somewhere in the universe?
We have a fantastic goal yet for the next generation, which is to find planets that remind us of home.
I believe we're right on the brink of having the technological capability to actually answer a question that humanity has been asking itself for the last 2,000 years.
Another Earth could be as close as our nearest star system.
We're right on the threshold of being able to find these planets.
There could be twisted Earths under bizarre suns. Can we find these other Earths as they float hidden in the billions of stars and trillions of planets of the universe? Is there another Earth in the universe? It's perhaps one of the oldest ideas since mankind was able to look up at the stars and wonder.
back when people were sitting around their campfires and looking up at the stars and imagining them as other campfires with other tribes around them.
What exactly do we mean by another Earth? It should support Earth-like life.
When you boil it down, life needs three very basic things to exist. It needs a liquid medium of some sort to do its chemical reactions in. And we think water is the most likely liquid medium. It's very prevalent in the universe. We also need to look for the basic building blocks of life, the molecules that can help to put life together, the phosphorus in your DNA. And we need to have an energy source. It turns out that a terrestrial planet that has water on it pretty much has all of those things we need.
Not all planets capable of supporting Earth-like life would have to be carbon copies of our own Earth.
So you can think of it like a series of different types of houses. If you go into a city, for example, there will be grand mansions, and there will be smaller, more modest little two-bedroom homes, and there'll be city studios and skyscrapers and so on and so forth. All of these house people, all of these can help house life. And so we think about that when we go out into the universe looking. We're going to be looking for houses of all different kinds and keeping our minds open as to what could support life.
Astronomers have found over 300 exoplanets, that is, planets outside our solar system. The vast majority are gas giants, which are easier to find than small terrestrial planets like our Earth.
To build instruments to analyze those Earth-like planets, we have to anticipate ahead of time what the chemicals might be in that Earth-like atmosphere. For that reason, we need theory, we need models.
Victoria Meadows is in the planet modeling business. She heads up the Virtual Planet Laboratory at Seattle's University of Washington. The group, spread across institutions around the country, builds worlds that may exist in the yet unexplored universe.
The Virtual Planetary Laboratory allows us to simulate what planets might look like from space and what their environments might be like in advance of actually discovering these things out there in the universe. So it allows us to explore what planets might be like.
In the Virtual Planet Lab, fantastic worlds can be built, like a science fiction novelist with a supercomputer as a writing partner.
So we can take something that's like the Earth, but we whip away the sun, and we replace it with a star of different size and temperature. So what we've done with the Virtual Planetary Laboratory is modeled planets that started out as Earth-like and put them around stars that were much hotter with much stronger UV radiation, for example, than our own sun.
The models can produce bizarre alternate Earths filled with plants that are bright red, orange, or even pitch black. Photosynthesis can vary greatly depending on the light of the star that's shining on it.
Planets around F stars, for example, where the light from the star is much bluer, the plants there will tend to absorb more blue light, and so those plants could potentially be more likely to reflect red, orange, and yellow light, and so will appear red, orange, and yellow to us.
Plants on a world around weaker stars could evolve their coloration to use every bit of energy falling on them.
If you go down to much cooler stars than our sun, to M stars, plants on planets around M stars might in fact be black because they want to absorb as much light as possible to do their photosynthesis and to feed.
And then there's the water world planet, a theoretical Earth circling a volatile M-type star that constantly hits the planet with outbursts of deadly radiation.
And how does life cope on the surface of that planet? Is it possible to have life even when you have a flaring M star? It turns out that you can actually live about 9 meters underwater on a planet around an M star and still escape the worst of the flares, but still have enough light to be able to do photosynthesis and to survive.
Everything looks good from here.
And as future exploration missions are being drawn up, many scientists are focusing on what it would take to detect the byproducts of life on a distant planet.
Life produces gases. Life stinks. You can smell it. And we're going to look for those gases with these high-resolution spectrometers.
So what we really need to do is take the light from another Earth-like planet and analyze it to find out what the chemical composition of that atmosphere is.
Finding the locations of planets is something that UC Berkeley astronomer Jeff Marcy is very good at. He and his astronomy colleague, Paul Butler, are credited with finding more exoplanets than anyone else.
A planet that's farther from its host star will be very cool. And so there's a domain in between that we sometimes call the Goldilocks zone or the habitable zone, where the temperature is just right. And by just right, I mean lukewarm, so that water would be in liquid form. And of course, it's liquid water that's the prerequisite for life.
When we look at other planets and we ask, could there be life on other planets? My first question is, could that planet support liquid water? Yes, I'm interested. No, I'm not interested. It all comes down to show me the water.
Water is an amazing substance. We are frankly fortunate that the universe has something called water. It's the great cosmic cocktail mixer. Water is the critical stuff that allows the chemical reactions to take place that eventually lead to life.
But this special zone, where liquid water can exist, varies from place to place. If a star is a hot O type, the zone will be farther out from a sun. If it's a cool M type, the zone will be closer in. And it even changes with time. Stars are not stable. Even our own comfy habitable zone here on Earth will change in a few million years when our sun grows older and much hotter. Current technology doesn't exist to take pictures of distant exoplanets. So astronomers use the solar system star as a sort of proxy for a planet, since both were formed from the same planetary disk of material.
How do we know what a star is made out of? We don't go there and sample it. Your experiment would melt.
Astronomer Wes Traub heads up the effort by NASA's Jet Propulsion Laboratory to come up with the next generation of instruments that will look at planets outside our solar system.
What we do is we just simply look at it and we break the light up into different colors. This was done several hundred years ago by Newton. He discovered that if you put a prism in a ray of sunlight, it breaks it up into blue, green, red. And you look at these different colors and you discover something very startling all of a sudden. There are parts where colors are missing, and these missing colors are a fingerprint of the constituent of the sun that you're looking at.
With current technology, we can't directly view a spectrum of a planet outside our solar system. But eventually, more powerful instruments will allow us to use the same technique to fingerprint a planet for evidence of life.
If we look at that light from the planet and break it up with a prism or something similar, we can tell what the planet is made out of, and that's how we know whether our planet has oxygen, like our atmosphere, whether it has water vapor in the atmosphere, whether it has ozone, carbon dioxide, and nitrous oxide.
But nothing in the universe stays the same over time.
When our Earth formed 4.5 billion years ago, it had a very different atmosphere than it has now.
It's a challenge that Meadows and her team anticipate as they build their models of other Earth-like planets.
We would be very short-sighted to look just for an oxygen-rich planet at the same stage of development. So the thing is, when we go out to look for habitable worlds, they could all be extremely different. They could be very diverse.
And if we find another Earth, what are the chances we'll find a civilization on it that we can communicate with? What's the number of intelligent civilizations that might exist on other Earths in the universe? What would have to go into such a calculation?
How many stars are there? How many of those stars have planets? How many of those planets are close enough to have water? And on and on.
That's a problem that astronomers Carl Sagan and Frank Drake took on decades ago. Drake came up with an equation that estimated that up to 1 million civilizations may exist in just our Milky Way alone.
The Drake equation is this series of numbers that are trying to be put together in such a way to give us a kind of way of even closely estimating how many other intelligent civilizations are out there.
Peter Ward, a professor of biology and geology at Seattle's University of Washington, thinks the Drake equation greatly overestimates the number of advanced civilizations that could exist on other Earths in the universe. Ward and astronomy professor Don Brownlee's book, Rare Earth, explains why they think complex life, animal life like humans, may be rare in the universe.
We began to think that it was just too simplistic, that there's other stuff involved.
Ward cites a number of factors that he thinks would lower the original Drake estimates of how much complex life could exist in the Milky Way, and by extension, the universe.
First of all, plate tectonics. Plate tectonics is continental drift, and one wonders why would that have anything to do with the frequency of life on the planet? Plate tectonics also produces a recycling of elements, and that recycling does some very fundamental things. The most fundamental thing it does, it produces a temperature gauge. It's like a thermostat on the planet. If we get too warm, plate tectonic processes help us cool off.
Then there's the presence of metal on the planet.
Secondly, if you want to be an intelligent civilization, you better have metal. Metal's hard to find on a planet like Mars or Venus. But plate tectonics rotates everything, causes cracks, up come the heavy metals. What else do we need? We need a good Jupiter.
Having a gas giant like Jupiter, with its strong gravitational pull and the outer reaches of a solar system, protects the inner planets, those potential Earths, from frequent catastrophic impacts.
And the reason is those Jupiters sweep up gravitationally the asteroids and the comets, flinging them away, allowing the Earth to survive without so many impacts by that debris. And so it's those protective Jupiters that allow life to proceed without impacts by these asteroids and comets that would cause mass extinctions, as indeed happened to the dinosaurs.
65 million years ago, an asteroid hit Earth and wiped out most of the dinosaurs on the planet.
Those dinosaurs went out because Jupiter failed on the job and should have been fired. Bad Jupiter that day. It let one of these asteroids sweep by, but we've seen what it usually does. Comet Shoemaker-Levy that smashed into Jupiter at the last part of the last century. That's what Jupiter generally does. So good Jupiters are good things to have, and you can make equations for this.
When considering the habitability of planets, most astronomers place great emphasis on finding worlds in the habitable zone around a star. But Ward and his co-author believe that a planet's position within the larger galaxy is also critical.
So that's why we have defined, or did define, something we call the galactic habitable zone. That area within a galaxy, not too close, not too far. It's a Goldilocks area within our galaxy that's just right.
They came up with 9 factors that make up a so-called galactic habitable zone. Earth's position in the galaxy was considered. Away from killer neutron stars, black holes, and deadly gamma ray bursts. They included the percentage of stars that have planets and the percentage that have microbial life. They even estimated how often planets might have all their life extinguished. Earth itself may have narrowly missed such an event in 1998. Then, a high-density star called a magnetar burped out a flare of deadly gamma rays, unleashing as much energy in 0.2 of a second as the sun will put out in the next 100,000 years. Luckily, the magnetar was located 20,000 light-years away from Earth.
A really good question would be to ask, what would have happened had that magnetar that burped not been 20,000 light-years away, but 10,000 light-years away? Could there be a case where we had something within a few hundred light-years? If that were the case, new calculations suggest it could punch our atmosphere off, woof, in one burst. And you go, I can't breathe. Now that's catastrophic, and that is totally possible.
Humans may be just a cosmic fluke in the universe. The optimistic assumptions of the Drake equation may just not hold up with what astronomers have learned in the past decades.
The Drake equation was a fantastic construct, but it was done in the 1960s. We know so much more now. So we've added in stuff that wasn't known then. And I think it makes it more accurate. But ultimately, it also brings down the numbers. And the million civilizations I do not think can be supported by current understanding.
So how many other Earths supporting advanced civilizations does he think may exist in our Milky Way?
I've been asked over and over to make a prediction, and I'd say, well, we know it's at least one. It's more than one, I think. But I think it's more than one, but way less than a million.
Locating another civilization may happen as astronomers concentrate on looking for other Earth-like planets. But finding those Earths in the first place is a huge technical challenge for scientists. Unlike the stars that have been cataloged, planets can't be seen using current technology. A planet, when examined from light years away, is almost on top of its sun as viewed from outside our solar system. And to make matters worse, an Earth-like planet, even one many times larger than our Earth, reflects only an infinitesimal amount of light compared to its star.
So here we have a bright star and a planet which is 10 billion times fainter. It's hard to imagine what 10 billion times really is, but the way many of us think of this is, suppose you have a firefly, a very small firefly, a very weak light, and suppose that firefly is orbiting around or flying around a lighthouse. And suppose you're trying to look at this firefly flying around this lighthouse from 3,000 miles away. That's something what it's like.
Let's assume you could find that speck of a firefly from across the country, and then you had to figure out what that firefly is breathing by analyzing the gas it's exhaling. That's the challenge that faces an astronomer who first has to find a planet, then figure out how Earth-like its atmosphere is. But astronomers have figured out indirect ways to find extrasolar planets.
If that were the star, and very bright, and this were the planet, and it moved in front of that star, the star would get dimmer, and you would notice that.
It's called the transit method of discovering a planet, since it depends on seeing the travel or transit of a planet across a distant star.
The amount of light it blocks when it's in front tells us how big the planet is. So we use that to understand whether it's a small planet like Mercury, a planet like the Earth, or a huge giant like that of Jupiter. And we use the orbital period and the temperature of the star to tell us if it's in the habitable zone.
The orbital period is how long a planet takes to go around its star.
Then we'd go on its way and come back again a year later and do it over again.
When that period is combined with the type and size of the star, the information will tell scientists if the planets that are found are potentially in a habitable zone. The transit method works if the observer or the telescope is in the same plane as the star and its planets. But if you're above or below the system, another technique called the radial velocity method might be used. That method depends on careful observations of a distant star to watch if it's being gravitationally tugged back and forth by an unseen exoplanet. Astronomers can use that information to figure out details about the exoplanet that's influencing the star. Equipped with these tools, astronomers are finding hundreds of planets, some never dreamed of in astronomy textbooks. Super Earths, hot Jupiters, and even some close cousins to our own Earth. In the search for other Earths in the billions of stars in the universe, astronomers have found a relationship between the composition of a star and the probability that it may have planets, both Earth-like and otherwise.
The stars that have heavier elements in them, the iron and the nickel and the silicon, have heavier elements for a good reason. Those stars formed out of molecular clouds in the Milky Way galaxy that collapsed down to form the star, and in so doing, left some placental material around them that eventually coagulated into the planets. So it makes sense that stars that formed with lots of heavy elements will form planets that also have lots of heavier elements.
Astronomers call the proportion of heavy elements in a star its metallicity. But that doesn't necessarily mean it has a lot of metal in the conventional sense.
Metal, for an astronomer, is any element that's heavier than hydrogen or helium. So in astronomer speak, lithium is a metal, sulfur is a metal, chlorine is a metal, and not just elements like iron, gold, and silver.
An Earth-like exoplanet not only needs heavy elements in its composition and to be in a star's habitable zone, it also needs to be the right size to sustain life. Right size means it can hold on to its atmosphere and have plate tectonics and volcanoes, both considered critical to regulating a planet's temperature. To do all this, astronomers estimate that the smallest a planet can be is 1/3 of Earth's mass. On the high side, a habitable planet cannot be greater than 10 times our Earth's mass. The very existence of exoplanets has gone from theory to reality only in the last decade.
A little over 10 years ago, we had no known extrasolar planets at all. The only planets we knew of were those orbiting our sun. And now we know of planets orbiting other stars. And of course, what's really exciting about these planets is that some of them may be habitable, and so there's a chance that there's life on some of them.
Of the hundreds of exoplanets found, some may not follow the familiar blueprint of planets in our solar system.
We found these bizarre Jupiters that orbit very close to their star. They're blowtorched hot, and these Jupiters undoubtedly got close to their star by migrating inward.
Sometimes the formation of a Jupiter-mass planet can be kind of a death knell for terrestrial planets in the system.
And what if we had been unlucky enough to have such a Jupiter in our solar system?
It would have slingshot the Earth right out of its orbit into the vast, cold darkness of outer space, and the Earth would eventually die off as a cold, dark hulk.
Over 300 exoplanets have been discovered, and more are being found all the time. But the majority are monstrously huge gas giants that hold little promise of being truly Earth-like. In the Pegasus constellation, some 50 light-years from Earth, the planet 51 Pegasi b can be found. It was the first planet discovered outside our solar system. A gas giant as big as Jupiter, but orbiting much closer to its star. It races around its sun in just 4 days. The planet 70 Virginis b is even farther away than Pegasi, at 60 light-years. It's 7.5 times as massive as our Jupiter. At first, it was believed to be in the habitable zone of the star, so it was nicknamed Goldilocks. Later calculations showed that it had an eccentric orbit that brought it to within 27 million miles of its sun, which is roasting hot, so it's no longer considered to be in a habitable range. The massive gas giant Trace 4 is over 1.5 times the diameter of our Jupiter, making it the largest planet found so far. It's 1,400 light years from Earth. This gas giant, even though it's much larger than Jupiter, only has a little over 3/4 of its mass. It's a hot Jupiter, zooming around its sun in only 3.5 days. Astronomers haven't been able to find true Earth-like planets outside our solar system because they've not yet been able to detect such relatively small rocky planets as our Earth. The technology is just not there yet. But astronomers are having more luck finding what are termed super-Earths.
People actually being able to discover planets that could potentially be in the habitable zone around other stars. And one classic example of this is a planet called Gliese 581c.
The Gliese 581 system is located about 20.5 light years from Earth in the Libra constellation. Gliese 581c has 5 times the mass of our Earth. There were hopes that 581c would be the first Earth-like planet found in the habitable zone of a star, but that turned out to be wrong.
Probably it's a little bit on the wrong side of the fence. So that one, instead of being a super Earth, is probably a super Venus.
It's like our own Venus, way on the hot side, with possible 600-degree temperatures, but also more massive than Venus. But Gliese 581c has a relative a little farther out and cooler. It's named Gliese 581d.
And this one is at the far back end of the habitable zone, where it's quite cold. When you initially look at it, you think, well, maybe that's a bit too cold. But it turns out that if the planet potentially has enough greenhouse gases, it might be possible to make that planet warm.
Another promising Earth-like planet may be HD 69830d. This is a big planet, 17 times the size of our Earth. It's about 42 light years away from our solar system in the constellation Puppis.
HD 69830d is a potential planet where life could form because it has approximately the right temperature.
The planet could have a temperature between that of Venus and Earth, and it has a close to circular orbit, meaning it won't get toasted by close encounters with the star it's orbiting.
So you can have liquid water. The mass of the planet is maybe not so good. It's about 17 times the mass of the Earth, which could be a solid ball of rock, or it could also be a gas ball like Neptune in our solar system.
When NASA's able to fly future planet-finding missions, it's expected that astronomers will be able to get a spectrum that will give us much more information about the composition of the planet. They may be able to figure out if the planet has a solid surface, or that it's a water world, or perhaps something else entirely. The search for other Earths has taken astronomers light years from our neighborhood in space. But could another Earth exist in our own solar system? While astronomers look at star systems many light years away in hopes of finding another blue marble of a planet, other Earths may be a lot closer than that.
So imagine going back 3.5 billion years ago and visiting our solar system. You'd have seen 2 blue marbles here. Earth, water, thick carbon dioxide atmosphere, warm conditions, life. Now imagine moving a little over, you see Mars. Water on the surface, thick carbon dioxide atmosphere, warm conditions, possibly life. Well, the 2 planets start evolving. Earth stays habitable. Mars doesn't.
Both Venus and Mars are just on the edge of the Goldilocks zone of habitability. Both may be cases of failed Earths. Once you fall off that path, you may never be able to come back.
Mars is a lesson for what you need to maintain habitability for a long time. And the answer, we think, turns out to be big. You have to be as big as the Earth to maintain habitability for a long time. Mars is too small. Being too small, it has no way to recycle its elements and has no way to hold on to its atmosphere for a long time. So size matters.
And while Mars is now too cold, Venus, our other would-be Earth, has the opposite problem. It's too hot.
It was a little bit too close to its star, too close to the sun. It got hot and it stayed hot. And so all the carbon dioxide, the CO2 and so on, that formed on Earth, formed also on Venus. But on Earth, it was incorporated into rocks. On Venus, it stayed in the atmosphere. And the atmosphere basically is global warming to the nth degree. Sunlight comes in and it just doesn't leave. That planet is like the inside of a pizza oven.
Venus failed because it was born in the wrong place. Mars failed because it was born the wrong size. So we have an interesting story here, Venus, Earth, and Mars. Venus is in the wrong place. Mars is the wrong size. Earth is the right place and the right size.
So if the planets in our solar system aren't great candidates for being Earth-like, our closest galactic neighbor, Alpha Centauri, may harbor an Earth-like planet. At a little over 4 light-years away, in galactic terms, it's next door.
I think that there's a good chance that Earth-like planets are orbiting around either one or both stars in the Alpha Centauri system.
Astronomer Greg Laughlin has done computer modeling to show that Earth-like planets should exist in the system.
There's a number of reasons why Alpha Centauri is the best star in the sky for hunting for Earths. Alpha Centauri is very close by. Alpha Centauri has 2 sun-like stars. Alpha Centauri has a large quantity of the kinds of heavy elements that go into building planets.
How close is the Alpha Centauri system to us? First, imagine shrinking our sun down to the size of a grain of sand.
A grain of sand is just about the smallest object that you can see with your eyes and just about the smallest object that you can actually feel with your fingers. And at the scale where the sun is the size of a grain of sand, the Alpha Centauri system is 3 more sand grains placed about 5 miles away. Now, if we wanted to get a similarly good system to Alpha Centauri, we'd have to actually go all the way over the horizon to find another stellar system that's good.
And it turns out that the stars of the Alpha Centauri system should have plenty of raw materials to make planets out of.
Alpha Centauri has a higher metallicity than our own sun does, and that implies that planet formation was a process that took place relatively easily in that system.
And last but not least, Alpha Centauri's 2 main stars provide an additional benefit.
The initial indications show that there are no Jupiter-mass planets in the Alpha Centauri system. That makes it more straightforward for terrestrial planets to form around either or both of the stars.
That's because large gas giants form around cores of ice that are as big as our entire Earth. So these giants need a lot of cold space to form these cores. Think of how far out Jupiter is from our sun. However, when you have 2 stars with overlapping orbits in a system like Alpha Centauri, there isn't a space in the system that's big enough and cold enough to allow the formation of these gas giants.
So we expect that the planets that exist in the Alpha Centauri system, if they're there, they're terrestrial planets like the Earth or Mars or Venus. They're not gas giant planets like Jupiter or Saturn.
What if we could actually survey how many Earths are in our part of the universe? What if we could peer directly into the atmosphere of another Earth that was light years away? In order to find another Earth, astronomers have to eventually overcome the huge technical challenges of how to view a distant planet. It's a problem that NASA has tackled much like the race for the moon, with plans that stretch out over decades. The first exoplanet-finding mission will be Kepler, which launches in 2009. The NASA Survey project is named after the 17th century astronomer Johannes Kepler, who discovered the laws of planetary motion.
What Kepler will do is so utterly simple and yet extraordinarily powerful, it brings tears to my eyes. What Kepler will do is simply be a space-borne telescope and stare at the constellations Cygnus and Lyra, taking picture after picture after picture, with the goal of looking for stars that dim when an Earth-like planet blocks some of the starlight. And it will be the first time that we humans detect other Earth-like planets around other stars.
The principal investigator for Kepler is William Barucki. He's been championing the mission for 25 years.
Kepler basically is a space mission that puts up a very large telescope. It's very much like a camcorder. It's always taking pictures of these stars, sending that information back to you.
The mission is a comparatively small survey project to look at a fixed portion of the sky for an initial time of 3.5 years.
The main result from Kepler will be to give us a statistical count. It's a head count of what the population is. You know, how many small planets do you have and how many large planets do you have?
Kepler's results will in turn be used to help decide what will be built for the next generation of planet-finding missions.
Kepler really is one step along the way. It's to try to find Earths and find out whether they're frequent. If they are frequent, they must be close, so we can build a modest instrument. If we don't find many Earths, what that means is before you're going to find another one, you're going to have to look a huge distance into space. So you're going to have to build a much bigger, much more expensive instrument.
The most majestic, spectacular telescope ever conceived by humanity is something called the Terrestrial Planet Finder. It will be an enormous telescope in space, frankly probably costing several $1 billion, but what it will do is absolutely unique. It will be the first telescope to take pictures of other Earth-like planets.
To directly view a planet outside our solar system, a whole new telescope technology is being developed.
To construct the Terrestrial Planet Finder that will image Earths against the glare of their host stars, we need some entirely new optical technology. A technology that, frankly, we haven't invented yet. The frustration is just palpable that we actually know vaguely how to detect other Earths, but we don't know exactly how to build the optics to do so.
NASA envisions the Terrestrial Planet Finder as a suite of two very different but complementary advanced concept telescopes. The first, the visible light coronagraph, consists of a large optical telescope with a mirror at least 100 times more precise than the Hubble Space Telescope.
A coronagraph is a single telescope which collects the light from a star and focuses the light at the back end like a normal telescope. Except at that point, we block the light from the star and we try to let the light from the planet come through. By doing this, you cancel out the scattered light in the instrument, and so you allow yourself to be able to look at this planet, which is 10 billion times fainter than the main star.
The second terrestrial planet finder mission will be an interferometer.
An interferometer works by taking the light from a star that comes in and capturing it with 2 telescopes, sometimes more. And this combined light can be arranged in such a way that the light from the star disappears. That's good in the sense that you now can look at the planet that's next to it, and the light from the planet does not disappear. That's the magic of an interferometer.
To get all this done, new levels of precision in control and command technologies need to be perfected. Something that could take years to develop. The quest for the holy grail of astronomy, another Earth outside our solar system, has pushed scientists to speculate about how such a discovery could affect us.
I think if we find another Earth out there, that's going to have an enormous impact on society. I think to know that we are not alone, that we are one of many potential sites for life, I think will cause a huge paradigm shift in people's thinking.
But there's also the possibility that we may be unique in the universe, and that we may well find Earth-like planets, but no intelligent beings on them.
We have to remember something a little sobering. It is still possible that we humans are some fluke on the evolutionary tree, a twig, if you will. That happened on the East African savanna 2 million years ago, and those hominids somehow occupied a very rare niche that hadn't happened in 4.5 billion years on the Earth. It could still be that we humans are an extraordinary rarity in the Milky Way galaxy. In fact, it could be our destiny as a species to explore the Milky Way galaxy and be the first such explorer species. In which case, our destiny would be to find our roots, chemically and biologically, among the stars.
We have a TV picture now. Really looks beautiful.
In the beginning, there was darkness, and then bang, giving birth to an endless expanding existence of time, space, and matter. Every day, new discoveries are unlocking the mysterious, the mind-blowing, the deadly secrets of a place we call the universe. In the Star Wars universe, the Death Star is the ultimate weapon of mass destruction, able to annihilate entire planets. In the actual universe, the sky is filled with real-life Death Stars.
It can be thought of as sort of a time bomb.
Some are dangerously close to our planet.
Earth's life might take a bad hit when that radiation reaches us.
And one has the Earth in its crosshairs.
It was almost a shock. I didn't believe it when I first saw it.
They are the Death Stars, and they make the universe a very dangerous place. Thousands of light years from the Earth, a supermassive star is preparing to hit the self-destruct button. Stars explode every day in the universe, but this one is different. It lurks in the constellation Sagittarius, the mythological archer of the celestial zodiac. The star is called WR-104, and its destructive force could be targeting us and taking aim at our fragile blue planet with enough deadly radiation to ignite our protective ozone layer. This would incite drastic climate change, cause the extinction of many plant and animal species, and potentially the demise of mankind. WR-104 is just one of millions of massive Death Stars in the universe. These savage celestial bodies are aging giants, preparing to blast themselves into a stellar afterlife.
At that point, the outer layers of the star have nothing left to support them against gravity, so they suddenly fall inwards.
Their last breath can ignite the biggest explosion in the known universe. A gamma ray burst. A blast far exceeding the energy output of our own sun over its entire 10 billion year life. If one were to target the Earth, life as we know it could cease to exist. This is what could happen with WR-104, making it a real-life Death Star. In the film Star Wars, the Death Star is the dark side's ultimate weapon. The predatory star is pure science fiction, but the reality is much scarier.
A Death Star in real life is a star that blows up and blasts any nearby planets with deadly radiation. You know, that's a real Death Star.
WR-104 is what's known as a Wolf-Rayet star. They are the largest stars in the universe, hulking beasts 30 times bigger than our own sun, each of them counting down to Armageddon. Discovered by French astronomers Charles Wolf and Georges Rayet in 1867, Wolf-Rayet stars are the outlaws of the universe.
Stars live by the credo, live fast, die young, leave a good-looking corpse. And the bigger they are, the faster they live, and the faster they live, the more violent their end.
They burn through their nuclear fuel extremely quickly and exhaust everything that they have. And so consequently, they don't live very long, maybe a few tens of millions of years at most.
And they're easy to find because they're the real T-Rexes of the stellar kingdom. They're immensely powerful.
In the year 2000, Australian astronomer Peter Tuthill began studying Wolf-Rayet 104. Some 8,000 light-years from Earth, this giant was ominously different from the others. Tuthill's team immediately noticed an immense dust cloud around it, 20 times larger than our entire solar system.
We knew there was dust around Wolf-Rayet 104, and that was a puzzle because it's a bit like finding a snowflake in hell. There was a mystery there, and we wanted to try and solve that mystery.
Over the course of 6 years, Tuthill used an infrared camera at the Keck Observatory in Hawaii to create a composited image from multiple exposures. It yielded an amazing time-lapse sequence. 104 was producing an exotic spiraling plume of dust.
It was almost a shock. I didn't believe it when I first saw it. I thought, stars don't look like spirals. There's no spiral I've ever seen in a book. We then had a mad scramble. We had to try and understand how a star can produce this elegant tail.
Tuthill discovered that the key to this strange dust spiral was the fact that WR-104 wasn't alone. It's locked in orbit with a smaller star in what's known as a binary system. Both stars eject masses of charged particles called stellar winds. These winds aren't uncommon in the universe. Our own sun creates a solar wind that extends beyond the outer planets. The difference is that in a binary system, when winds from the two stars collide, gases are compressed and dust and soot are created. But what causes this dust to form into such an exotic spiral?
So it turns out that a lawn sprinkler makes a great analogy to illustrate the physics that's occurring in these colliding wind binary systems. We've modified this sprinkler so that it only shoots one jet out of the spigot.
The single water jet represents the constant flow of dust particles being created by the colliding stellar winds. But because the two stars in WR-104's system are in constant orbit around each other, it adds a circular motion to the stream of dust.
Your first intuition is that the water is moving in a circular motion, but in actual fact, the lawn sprinkler is really shooting a jet in a straight line. The water droplets, even though they're moving in a straight line away from the spigot, they create an arc, and that arc wraps into a spiral with the rotation.
The spiral spawned even more questions. The most troubling, exactly what kind of Death Star could WR-104 become?
Wolf-Rayet stars can be thought of as sort of a time bomb because they're so massive that they can't live for very long. And once they've burned up all of their nuclear fuel, there's nothing left to support the star against the relentless pull of gravity. And at that point, the core of the star collapses, and the outer layers fall in on top of it and bounce outward in a tremendous explosion.
The explosion is a supernova, an immense burst of radiation that briefly outshines an entire galaxy. Wolf-Rayet 104 will definitely go supernova sometime in the next few 100,000 years. At 8,000 light years away, the explosion itself poses no threat to the Earth. But there's a chance the supernova will trigger the most violent event in the universe, a gamma-ray burst. In a small percentage of these massive Death Stars, a gamma-ray burst is triggered by the crushing transformation of a dying star into a black hole.
As a star collapses, it produces a massive electric field. And in an instant, the energy from this electric field is turned into matter and antimatter particles, which then collide with each other and produce a huge pulse of energy.
They are the most powerful energy beams in the electromagnetic spectrum, more lethal than microwaves, infrared energy, and even X-rays. Humans have learned to harness deadly gamma rays for useful purposes, such as food irradiation. By using gamma rays, food processors can eliminate microorganisms, bacteria, viruses, and insects. But the amount of gamma radiation applied is an extremely tiny fraction of the energy released in a stellar gamma-ray burst.
Gamma-ray bursts produce so much radiation that if we were to create a gamma-ray burst on Earth, it would be like a huge number of nuclear bombs going off. It would be devastating for life on Earth.
For the human race, the most critical piece of information about gamma-ray bursts is the direction of fire. At the moment of collapse, the star becomes a dense, flattened disk, and the rotational axis poles are its only openings free of dense star matter.
You get two relatively evacuated regions along the poles, and it's along those directions that material can be ejected because it encounters relatively little resistance. So this container of yogurt provides a nice analogy for what happens in a gamma-ray burst. I'm going to drop the container of yogurt, and because of the sides of the container, yogurt is not going to be able to go out along those directions. But the top of the container is open, so yogurt is going to squirt out along the top. Watch what happens. So the yogurt went squirting basically straight up. It couldn't go out the sides because it was blocked by the sides of the yogurt container. And that's a nice analogy for what happens in a gamma-ray burst.
The greatest concern for humans is the direction that the gamma ray burst is firing. If the axis of the collapsing star is pointing in our direction, we could be in serious trouble. When Peter Tuthill's team studied the plane of orbit of WR-104's dust plume, they came to a shocking realization.
This spiral was the key that unlocked a lot of these secrets. And where things start to get a little scary is that this system, at first blush, appears to be almost face-on. We're looking right down the axis at the heart. It's like looking at a plate, a dinner plate. If you take that plane and you tilt it to the line of sight, it looks inclined. You're no longer looking at a circular dinner plate.
Further examination suggests the rotational axis of the dust plume appears to match the rotational axis of the Wolf-Rayet star itself, meaning the Earth is staring directly down the barrel of a gun.
That means that if this star becomes a gamma ray burst when it blows up, one of the two jets will be pointing toward us.
The beautiful spiral of Wolf-Rayet 104 is suddenly a messenger of doom. Some 8,000 light years from Earth, two stars are locked in a gravitational dance. Their stellar winds ejecting a vast cloud of dust in a graceful spiral. But there's more to this star couple than just a beautiful tale. The larger of the two, Wolf-Rayet 104, is a massive Death Star on the verge of exploding as a supernova. That much is certain. The real mystery is, will it also unleash a gamma ray burst, or GRB, the most powerful burst of energy in the universe? The question is an important one for all on Earth, especially considering the star's axis may be pointing directly at us.
That means that when it blows up, if it becomes a gamma ray burst, the jet could be pointing straight at us.
WR-104 is counting down to destruction in the constellation Sagittarius. Named by Roman astrologers over 2,000 years ago, Sagittarius is Latin for the archer.
And you have to ask, maybe were the ancients onto something? Is there something to do with the archer aiming at us?
WR-104 can be thought of as an arrow pointing our way, if indeed it blows up as a gamma ray burst.
There is little dispute among today's astronomers that a tightly focused beam from a gamma ray burst will travel vast distances in space. In fact, on April 23, 2009, the Swift Multi-Wavelength Observatory, orbiting the Earth, recorded a GRB that occurred 13 billion light years away from Earth, near the very edge of the visible universe. The blast occurred only about 630 million years after the Big Bang. This means that gamma rays from the exploding star traveled at the speed of light for 13 billion years before they were visible to us, making this gamma ray burst the oldest stellar object in the known universe.
We know of no star or galaxy that's farther away than this gamma ray burst. It's the single most distant discrete object ever seen.
At only 8,000 light years, a GRB blast from Wolf-Rayet 104 could be catastrophic.
The flash that we would see if Wolf-Rayet 104 went off would be much brighter than the sun, especially at gamma ray energies. A single gamma ray burst can easily exceed the total light output of millions of galaxies. And each of those galaxies contains 100 billion stars.
This Death Star is a ticking time bomb. Scientists know for sure it will go supernova. But questions remain about its potential to unleash a gamma-ray burst in the direction of Earth.
That's the first point we need to establish. If it does produce a gamma-ray burst, is that gamma-ray burst pointing towards us?
The spiraling axis of the star appears to be aimed in the direction of Earth. But with thousands of light years to travel, would the GRB beam actually hit the target? Would the Archer's aim be true?
We know it's pointing roughly toward us, but it could be pointing sufficiently away that the beam of radiation from the gamma-ray burst, if it turns into a gamma-ray burst, will actually miss us.
However, if the star is aligned, one powerful burst of energy could turn the Earth's ozone layer into a radioactive inferno.
Even a gamma-ray burst that's thousands of light years away could deplete the ozone layer to roughly half of its current level. Now that won't kill all of the species, but it could lead to what we call a mass extinction, where a good fraction of all living species die rather suddenly.
So the burning question is, will the death of WR-104 really trigger a gamma-ray burst? Scientists just don't know. The mandatory requirement for a star to produce a lethal gamma-ray burst is high horsepower rotation. All stars rotate on their axes. Some massive stars can spin very fast.
So the rotating star, the rotational energy is part of what produces the gamma-ray burst.
If you can put the brakes on, if you can take that rapidly spinning star and slow it down before it gets to that stage, you've defused that bomb.
Based on mounting scientific evidence, it appears the universe itself is applying another set of brakes to its stars. It's called metallicity. Stars are primarily made of hydrogen and helium. But heavier, more complex elements are created every time a star explodes. Elements like carbon, nitrogen, and oxygen that then become the raw materials for the next generation of stars. So a star born today has more heavy elements, also known as a higher metallicity, than a star born earlier in the history of the universe.
When a massive star has a lot of heavy elements in it, it tends to lose a lot of its mass through winds. And if it loses a lot of its mass, it also loses a lot of its rotation. And it ends up rotating too slowly to form a GRB.
So something is happening to the Wolf-Rayet stars today that's going up there and defusing all the bombs. So they're still blowing up as supernovae, but far, far fewer of them are taking that supernova to the next step as a gamma-ray burst.
Could these brakes slow WR-104 enough to render it harmless to the Earth? Many astronomers believe so. But what if they're wrong? At 8,000 light years away, is Earth really in the danger zone? When the Death Star, called WR-104, finally explodes, it has the potential to unleash a deadly gamma-ray burst directly at Earth. It's believed the star is roughly 8,000 light years away from us. Is this close enough for a gamma-ray burst to do damage to our planet?
And being 5,000 to 8,000 light years away, it's in the danger zone. Earth's life might take a bad hit when that radiation reaches us.
If it was another 2 or 3 times further away, we'd probably be okay. And if it was 2 or 3 times closer, we'd really be shaking in our boots. But It's just at the edge of its range where one would expect, well, you know, it might do something, but it's probably not going to roast us all in our sleep.
So perhaps once every billion years or so, there's a gamma ray burst that's sufficiently close and sufficiently well pointing toward us that we need to worry.
Death stars of all sizes populate the universe. But stars are not the only entities capable of such violence. The universe is also home to death galaxies, like 3C321, also known as the Death Star Galaxy.
3C321 is a galaxy with a giant black hole in the middle, millions of times the mass of our sun.
Just outside the black hole's edge, the chaotic churning of magnetic fields and gravitational pull has ignited a high-energy particle jet. These jets are not uncommon, but this one is delivering a beating to its nearest neighbor.
The case of 3C321 is very interesting because there happens to be another galaxy 20,000 light years away. The stars in that galaxy are being blasted by the energetic particles and radiation from one of these jets.
X-ray astronomer Dan Evans has been tracking the Death Star Galaxy and its violent behavior from the Chandra X-ray Satellite Control Center outside Boston.
So we see black holes do kind of strange things, but only a very small fraction emit these powerful jets of particles. And a fraction even smaller, such as the 3C321 galaxy, the Death Star galaxy, smack into other companion galaxies. So that's incredibly rare.
The companion galaxy is across the galactic street, 20,000 light years distant. The massive energy beam, even larger than a gamma ray burst from a dying star, is firing non-stop with a seemingly limitless energy supply.
So what we're looking at here is the best terrestrial analogy for the Death Star galaxy, 3C321. A jet is racing out of the black hole, close to the speed of light, and it's actually normally would propagate up to about 1 million light years away. But in the special case of 3C321, that jet is slamming into the side of a companion galaxy. And in doing so, it's becoming disrupted and distorted and bent away. And that's wreaking all sorts of havoc for that companion galaxy.
Much like the building is deflecting the water jet, the planets and stars in the victimized galaxy are deflecting most of the attacking particles.
So this jet is actually a massive beam of energy and particles. And these particles have been superheated such that they form a plasma.
Plasma is a mix of super-hot, charged electrons and ions funneled into the jet by the black hole's immense magnetic field.
So jets that race out of black holes are actually incredibly energetic. And in fact, they can accelerate particles such that they emit light, maybe even up to gamma rays. These rays are incredibly powerful.
And very long-lasting. Some estimates say the energy jet from the Death Star galaxy has been firing for nearly 2 million years. For its fuel, 3C321 simply devoured an entire galaxy.
It's got a lot of fuel. What we actually think is happening here is that there's been a previous merger. So another galaxy has fallen in to the main galaxy. We can see this beautiful dust lane, which implies that the galaxy has been shredded already. And so that act of shredding drives mass down onto the black hole.
After consuming another galaxy's provision of plasma particles, the Death Star galaxy somehow energized the particles into a jet. Black holes have powerful magnetic fields and super fast spin rates, a combination that somehow ignites the particle jet. Scientists believe the reason the jets fire in one direction has to do with all the dust and gas circling the black hole.
In the case of an active galaxy like 3C321, which has a supermassive black hole in the center, you'll often have a donut or torus of material surrounding it. In that case, highly energetic particles near the black hole can't emerge from that region through the donut along the plane of the galaxy. They can only emerge along this axis where there's relatively little obstructing material.
Unfortunately for the companion galaxy, it's staring straight down the donut hole. And the jet's zone of impact is like the widely scattered blast of a cosmic shotgun.
The problem with this jet of high-speed particles and radiation hitting the little galaxy 20,000 light years away is that the jet is wide enough to encompass a large number of stars in this galaxy. So any creatures living on any planets, orbiting any stars in that galaxy, are in serious trouble right now.
What if it were our own Milky Way being blasted by the Death Star galaxy? Put Earth in the path of the jet, and the effect on the ozone layer would be enormous and deadly.
The gamma rays from the jet in 3C321 convert nitrogen gas into nitrous oxides, and it's those nitrous oxides that actually act as a catalyst in the destruction of ozone. So within a matter of weeks to months, maybe up to a year, the ozone layer will be completely obliterated. That's a nasty consequence.
But like many phenomena observed in the universe, there is a recurring paradox. From death comes life. 3C321 not only destroys, it also creates.
So one of my favorite things about 3C321 is it demonstrates really clearly that black holes don't just gobble everything up in the universe. They're not all complete harbingers of destruction. The jet that is coming out of 3C321 is hammering into the side of the companion galaxy. And yes, of course, that's a destructive force. But the ultimate legacy, actually, is that the gas clouds that get compressed during this interaction can actually form stars, and the stars can form planets, and the planets may even form life. So this is beautiful cycle of birth and rebirth and destruction that's synonymous with the universe and black holes.
One day in the future, our own Milky Way could form its own merger with the nearby Andromeda galaxy and create a new Death Star galaxy, a violent act that would certainly spell doom for the Earth. Such an event would likely occur many billions of years in the future. But there are other stellar threats streaking through our galaxy at high speed. They are hypervelocity stars, and nothing can stop them. To the human eye, stars paint a tranquil picture in the heavens above. But take an up-close look. A select few are Death Stars on the verge of extinction, and these cosmic beasts are anything but peaceful.
Eventually, a star will burn through all the hydrogen in its core and convert it all to helium. Once it does that, it has to be massive enough to be able to ignite the helium and convert helium into heavier elements like carbon, oxygen, and nitrogen. And this releases an enormous amount of energy. This process is the same release of energy that goes on inside a hydrogen bomb.
Though they are incredibly violent, most of these stars will one day burn up and slip quietly into the afterlife as stellar corpses called white dwarf stars, smallish balls of electrons and nuclei destined to never again burn brightly. But some are supermassive stars, so energetic they end in a fantastic supernova explosion, and sometimes even produce the largest of all blasts, the gamma ray burst. But for a few massive Death Stars, the end is a new beginning. Consider the second life of a neutron star. When a massive star explodes in a supernova, its core sometimes collapses to form a black hole. But much more frequently, if the core isn't massive enough to create the black hole, it forms something almost as weird, a neutron star, a small but incredibly dense body.
It actually has a huge amount of material compressed into a very small space. So you have, for example, the mass of our entire sun squeezed into a space maybe only a couple of tens of miles across.
The gravity is so strong that the protons and electrons inside the atoms of the star are actually pushed together to form neutrons. And a neutron star can remain stable for billions of years.
Neutron stars by themselves pose no danger to their celestial neighbors, unless they can find a partner.
You can also get another death scenario for stars where there's a sort of mutual suicide pact between two neutron stars.
These are called co-orbiting neutron stars, a phenomenon initiated when two neutron stars begin an intimate but doomed relationship. Their orbit narrows over millions of years until they finally meet in a flash of light.
And in so doing, they can generate a violent explosion, a second life in a sense.
So there's two different types of gamma ray bursts. There's short bursts, which have durations of less than 2 seconds, and we think that short bursts are produced by merging neutron stars.
The short bursts are different than the longer GRBs produced by collapsing massive stars. The gamma ray burst emitted by two colliding neutron stars may be short, but it's powerful, equal to the energy released by the sun over its entire lifetime in less than 2 seconds. The worry for us? At least 24 pairs of orbiting neutron stars exist in the Milky Way.
A very nearby gamma ray burst, first and foremost, would get rid of much of the ozone layer. That could have disastrous effects on Earth.
Some estimates hold that a violent neutron-star merger occurs within about 3,000 light-years of the Sun every 100 million years. That's about the same interval as the mass extinction events recorded in the Earth's fossil record. Is it coincidence, or should we worry that the last tango of two dying stars might eventually blast the Earth's ozone layer with deadly gamma rays and alter the planet? Scientists don't know the answer. The chances are probably about the same as a runaway star plowing headlong into the Earth. It's a remote possibility, but fearsome to contemplate.
You could actually have the possibility that a collection of stars that perhaps were all together in the same neighborhood interacting with each other sometimes ejects a star just to wander off on its own. As far as we know, there are no wandering stars headed our way, but if that were to happen, it could be quite interesting.
One scenario could see the Earth's orbit around the Sun disrupted by the gravitational pull of the wandering star.
One dramatic possibility is that such a wandering star simply kicks the Earth entirely out of the solar system. And so we're now wandering around without a source of energy, the sun. No one really knows what would happen. It really depends upon the angle of approach, the mass of the star, etc.
Wandering stars can travel up to 60 miles per second. Fast, but still not fast enough to escape the Milky Way's gravitational pull. But there are some supercharged turbo models that could actually break free and rocket out into the universe. These are called hypervelocity stars.
Hypervelocity stars are normal stars like the sun, except that they're moving out of the galaxy at well over 1 million miles an hour. And that's beyond the escape velocity of the Milky Way.
The need for speed begins with a normal pair of co-orbiting stars that get too close to the edge of a black hole. Just as the disabled Apollo 13 command module got a boost of velocity by maneuvering close to the moon's orbit, the hypervelocity star gets a huge gravitational kick from the black hole, severing the bond with its binary partner.
The star closest to the black hole is captured into a very tight orbit around the black hole, and so it loses this energy. The other star gains that energy and is ejected with this very large velocity as a result.
The ejection of a hypervelocity star is much like a slingshot effect. At the instant the binary star's orbit is broken, the hypervelocity star is launched with incredible force into the void of space.
They've been voted out of the Milky Way, and they're destined to drift into the inky depths of intergalactic space. It's very unlikely that these stars will ever affect the Earth.
Fortunately, the eventual death of these speedy stars will occur far away from our solar system. It's the death stars on our own block we need to keep an eye on. In cosmic time, their fuses are lit, and we have a front row seat to their annihilation. In remote corners of the universe, countless stars are biding their time on death row, sentenced to spectacular, violent endings. Closer to home, there are a few dozen stars within 20 light years of the Earth, and a few of these are preparing for death.
I think we're safe from the dangers of a normal supernova. In the case of a gamma ray burst, we're not so sure.
One is in the stellar system Eta Carina, a supermassive star about 100 times bigger and 1,000,000 times more luminous than the Sun. In 1843, a buildup of pressure ignited a gigantic eruption of light seen from Earth. But the star survived and formed a dust cloud called a nebula. At a distance of just 8,000 light years, we'll have a front row seat to its annihilation.
We think it's going to turn into a black hole sometime between now and the next 1,000,000 years. And as it collapses, it has enough matter that it can produce a powerful gamma ray burst.
Unlike the star, Wolf-Rayet 104, Eta Carina doesn't have us in its crosshairs.
We know that the rotation of Eta Carina is not pointed towards Earth. So lucky for us, the pulse of the gamma ray is not going to be directly impacting Earth.
When it happens, the explosion will likely be the brightest supernova ever witnessed by mankind. Unless the title goes to another Death Star contender that's even closer to Earth, Betelgeuse. Located in the Orion constellation, about 500 light years away, Betelgeuse is quickly burning through the last of its nuclear fuel.
Betelgeuse is a very massive star, about 20 times the mass of the Sun, and it's within 500,000 years of exploding.
People have been noticing that Betelgeuse has been changing a lot over the last decades. It's actually shrunk considerably, about 15%. What that means, no one is sure, but everyone's keeping an eye on it.
Some scientists believe Betelgeuse could unleash a gamma ray burst. People on Earth have little to fear if it does. Like Eta Carina, the star's axis points safely away from Earth. Not only that, but Betelgeuse may also have a built-in blast shield.
Its explosion will be relatively normal. It won't be a gamma ray burst because there's this thick hydrogen envelope in Betelgeuse, and that hydrogen envelope will probably prevent the jet of particles and radiation from emerging. There's too much material through which the jet of radiation would have to pass.
Betelgeuse will shine intensely for a brief moment, but it won't compare to the final moments of our nearest star, the Sun.
Average stars like our Sun have nice long lifespans, fortunately for us, and our Sun is about halfway through its 10 billion year lifetime, so it's about 4.5 billion years old. That makes it middle-aged.
Scientists estimate that the sun will live another 5 billion years. But our problems could begin much sooner.
Our own sun is very gradually getting brighter, getting more powerful.